Remember how I said that the sample has less dispersion and the population has more dispersion? Since the population has more dispersion than the sample, that's why the population has a higher mean absolute deviation than the sample. We have a list of numbers right here, and we have a list of numbers right here. The list of numbers that has the most dispersion will have the higher mean absolute deviation, and the list of numbers that has lower dispersion will have the lower mean absolute deviation, because as the dispersion goes up, the mean absolute deviation goes up along with it. So the reason why the population has the higher mean absolute deviation is because the population has more dispersion than the sample. Now you might be wondering why we didn't just find the mean of this column of numbers. Why didn't we just find the mean of the deviations? The problem is, if you try to add the deviations, they'll add up to 0. And that'll actually always happen, no matter what list of numbers you're dealing with. The deviations always add up to 0, because the negative numbers and the positive numbers cancel out. So if you tried to add up these numbers on your own, you would see that they add up to 0. And if you tried to add up these numbers, should also add up to 0. The reason that they don't is because we rounded the mean before we did the formula. We didn't use the exact mean. But if we did use the exact mean of 60.33, then these would add up to 0. Since the deviations add up to 0, that gets you to a dead end, because once you get to 0, it's not clear what step should be done next. So the formula ends up at a dead end, and you don't want that to happen. So what you do is you find the absolute values of the deviations, which makes all the numbers positive, and then the numbers don't add up to 0. And you can actually, which means since these numbers don't add up to 0, you can find the mean of these numbers, even though you can't find the mean of these numbers over here, since they add up to 0. And if we tried to find the mean of these numbers, they would add up to 0, and then 0 divided by 5 is just 0. Now, I said that the reason that we found absolute values is to make all of the numbers positive so that they wouldn't add up to 0. There's actually another way to make the numbers positive besides finding the absolute values, and that's what I'll show you next. I'm going to show you how to calculate two other measures of dispersion called the variance and standard deviation. And to find the variance and standard deviation, you have to actually find squared deviations. And before I show you how to find squared deviations, I'll write out the steps for the variance and standard deviation. Step 1, well actually step 1 and 2 are the same, so I'll just copy and paste them. Step 3 is squaring each deviation, instead of finding the absolute value of each deviation. And then step 4 is finding the mean of the squared deviations. And you actually use an adjusted formula if the data comes from a sample. I'll show you what I mean when we go through the steps. And then step 5 is finding the square root of your answer from step 4. If you stop at step 4 and don't go to step 5, your value is called a variance. If you do go on to step 5, then the answer you get from step 5 is a standard deviation. Let's find the variance and standard deviation of the entire population. Step 1 is finding the mean of the data set. We already have the mean of the population. We found out that the mean was 66. So we've already finished step 1. We've also already finished step 2 because we already have deviations. We already subtracted each number by the mean. We can move on to step 3, which is squaring each deviation. We need to make a new column of squared deviations. We're going to square each of these deviations. What that means is we're just going to multiply each deviation by itself. So first we're going to multiply negative 6 by negative 6. When you multiply a negative number by a negative number, you get a positive answer. So negative 6 times negative 6 is just 36. You get the same answer that you would have had if you had multiplied 6 times 6. Let's now do it with 18. 18 squared is 18 times 18. So just multiplying each deviation by itself. We get 324. Next we'll just multiply negative 1 by itself, which will be negative 1 times negative 1. Negative 1 times negative 1 is just 1. The negatives cancel out. Negative 10 times negative 10. That's the same. That gives you the same answer as 10 times 10. The two negatives cancel out, and you get, well, 10 times 10 is 100. Now we have negative 1 times negative 1 again. Which is just 1. So now we have all of our squared deviations. We'll put them in here. So now we finished step 3. We've squared each deviation. The next step is finding the mean of the squared deviations. I mentioned an adjustment here. We actually don't do any adjustment if the data comes from an entire population, like it does here. We just find the mean of the squared deviations. So how do we do that? Well, the mean of the squared deviations will just be the total of the squared deviations divided by 5. It's just the mean of these 5 numbers. So let's add those 5 numbers and divide by 5. Let's add the 5 numbers and then divide. We're going to add the squared deviations and then divide the total by 5 since we have 5 squared deviations in here. So the total is 462. Now we divide 462 by 5 and we get our answer. We get 92.4. So the variance is just the mean of the squared deviations. Just like how the mean absolute deviation was the mean of the absolute deviations, the variance is just the mean of the squared deviations. And it came out to 92.4. Sometimes I like to write out the work like this. For the mean absolute deviation and the standard deviation. For the mean absolute deviation and the variance. Remember, we just added and divided by 5. Oh, it was 92.4. That was the variance. So to get the variance, we added the squared deviations and divided the total by 5. Because I said if you stop at step 4, you get the variance. If you stop at the mean of the squared deviations, you get the variance. If you go one step further and find the square root of the variance, you get a number called the standard deviation. So this was our variance. If we find the square root of the variance, we get the standard deviation. To get the square root, we can just press the square root key right here. And it comes out to about 9.61. So this is the standard deviation. I can just write STDEV And remember that this right here was the mean absolute deviation. I'll just write it like this. Now let's try to find the variance and standard deviation of the sample. We've already done steps 1 and 2 because we already have our deviations. We can skip to step 3, which is squaring each deviation. So we need our column of squared deviations. So we'll start with 0, which is the first deviation, and square it. 0 times 0 is just 0, meaning 0 squared is 0. 5 squared, which is 5 times 5, is 25. And negative 4 squared, which is negative 4 times negative 4, is 16, because the negatives cancel out. So we finished step 3, we squared all the deviations. Now we have to do step 4. Remember when we found the variance of the population, we just found the mean of the squared deviations in step 4. But notice how it says if it's a sample, you find an adjusted mean. And the way it's adjusted is actually, instead of dividing by the number of numbers, which would be 3, you divide by 1 less than the number of numbers. That's what makes it an adjusted average, or an adjusted mean. So let's add the squared deviations. They add up to 41. We divide by 1 less than the number of numbers, which means we divide by 2, because 2 is 1 less than 3. There's actually a notation for this. It's actually called n minus 1, because n is the number of numbers, so n is 3, and what we're dividing by is 1 less than n. So we're dividing by n minus 1. And we only divide by n minus 1 if the data came from a sample. If the data came from a population, you just divide by the number of numbers. You just divide by n. 41 divided by 2 is 20.5. That's the variance of our sample. And if you want the standard deviation, you just move on to step 5, which is just finding the square root of the variance. What's the square root of 20.5? We can hit the square root key, and it's about 4.53. So this is our standard deviation. Remember how I said that the mean absolute deviation was higher over here? I mean, the mean absolute deviation was 3 here, and it was 7.2 over here. And the reason why it came out to a higher number with the entire population is because the population had more dispersion. The idea is that with any measure of dispersion, the value should come out to a higher number when the data set has more dispersion, which means that since the variance and standard deviation are also measuring the dispersion, the variance and standard deviation of the population should come out higher, and the variance and standard deviation of the sample should come out lower, because the population has more dispersion and the sample has less dispersion. And let's check to see if that happened. The variance of the population is 92.4, and the variance of the sample is 20.5. So the variance of the population did come out higher because it has more dispersion, and the standard deviation of the population was 9.61, and the standard deviation of the sample was 4.53. So the standard deviation of the population did come out higher than the standard deviation of the sample. The reason why is because the population has more dispersion and the sample has less dispersion. So we can see that anytime you calculate a value to measure the dispersion, the value will come out higher when the data set has more dispersion. Or at least that's true with with all of the good measures of dispersion. The exception was the range. We could see that the range doesn't always come out to a higher number when the data has more spread, but the other three, the mean absolute deviation, variance, and standard deviation, will come out higher when the data has more spread. It'll always come out higher when the data has more spread. Now, since the variance and standard deviation over here used a slightly different formula than the variance and standard deviation over here, there's actually different terms or different words that are used. When you have a data from an entire population and you calculate the variance without using the adjustment in step 4, your answer is actually called a population variance. I can just write POP for population, and if you find the square root of that variance, then your answer is called a population standard deviation. And if you have data from a sample and you do use this adjustment in step 4, your answer right here would be called a sample variance. And when you find the square root of the sample variance, your answer is called a sample standard deviation. So it's just a more specific way of describing these values. So one reason why they use different words is because these values right here are calculated with a population, and these values are calculated with a sample. And another reason is because these values right here are calculated with a slightly different formula than these values over here. Now let's talk about why there's this adjustment when you have data from a sample. When you calculate the variance or standard deviation to measure the spread of a sample, the goal is to get a rough idea or to estimate the spread of the entire population. In other words, the purpose of calculating the sample variance or sample standard deviation is to try to get a rough idea of what the population variance or population standard deviation equals. So the sample variance right here is meant to estimate the population variance over here, and the sample standard deviation here is meant to estimate the population standard deviation over here. A sample value estimates the population value, and we see right here that the sample values came out smaller than the population values, and the reason why is because the sample had less dispersion than the entire population. And when you take a sample from the population, this actually tends to happen often. There's actually a tendency for samples to have less spread than the populations they come from. The reason why is because samples don't capture all of the extreme values that are found in the entire population. Just like how this sample didn't capture the extreme value of 84. So what this means is that if you don't use any adjustment, your sample variance and sample standard deviation will tend to underestimate the population variance and standard deviation because of the sample having less spread than the population. And what this adjustment is meant to do is to bring up the sample variance and standard deviation to a higher number. It's meant to boost them up higher so that they're closer to what the variance and standard deviation equal for the entire population. So if we didn't do this adjustment and we calculated the variance and standard deviation the same way as we did over here, these values would come out even smaller, which would mean that they would be even further below the population values. So when you divide by one less, you're dividing by a smaller number. And when you divide by a smaller number, you get a bigger answer. And when this comes out to a bigger answer, then this also comes out to a bigger answer, which means that these two values are, by using this adjustment, these two values were brought up closer to what the population values equal. So they're not these two values right here aren't underestimating these values as much as they would be if we didn't use that adjustment. And the reason why there's no adjustment for the mean absolute deviation or the range is because no adjustment has been developed because these values are pretty much never used to measure spread. Really only the variance and standard deviation are used in actual research. Actually, if you're reading journal articles about the results of psychological studies, the only value out of these four values that you'll usually see is the standard deviation. You'll usually see the mean and the standard deviation together. So the standard deviation is what's almost always used to measure spread in psychological studies. I wanted to talk a little bit more about the advantages and disadvantages of these different measures of dispersion. We know that the range has the disadvantage of only measuring the distance between the highest and lowest values. And the variance also has a disadvantage. The disadvantage of the variance is the squaring makes it come out to a fairly high number. And since it comes out to such a high number, it's difficult to understand what it's really showing about the data. The advantage of the mean absolute deviation and the standard deviation is that they give you an idea of how far the data values are from the mean. Let's talk about what I mean by that. Each of the absolute deviations is just the distance between a certain data value and the mean. This row has an absolute deviation of 6, and what this absolute deviation of 6 is showing is that this data value of 60, this person's data value of 60 is 6 away from the mean of 66. What this absolute deviation of 18 is showing is that this person's data value of 84 is 18 away from the mean of 66. And this person's data value of 65 is showing that this person's data value is 1 away from the mean of 66. So each of the absolute deviations is just the distance from a certain data value and the mean. And if you calculate the average or the mean of the absolute deviations to get the mean absolute deviation, what you found is just the mean of all of the distances. So it's really just the mean or the average distance from each data value to the mean. What this mean absolute deviation of 7.2 is saying is that the average distance between each data value and the mean of 66 is 7.2. So the mean absolute deviation literally is the average distance from each data value to the mean. And notice how the standard deviation comes out to a number close to the mean absolute deviation. If we look at the population of 5 people, the mean absolute deviation is 7.2, and the standard deviation is 9.61. So since they come out close to each other, you could say that the mean absolute deviation is the average distance from each data value to the mean, and the standard deviation is a number that's roughly showing the average distance from each data value to the mean. The same thing with a sample. The mean absolute deviation right here is the literal average distance from each number to the mean, because if you take these numbers right here, the absolute deviations, and you average them to get the average of 3, you get the average distance from each data value to the mean. And then if you calculate the standard deviation, you get a number close to the mean absolute deviation. So once again, the mean absolute deviation is the average distance from each data value to the mean, and the standard deviation is a number that roughly shows the average distance from each data value to the mean. So you could say that the mean absolute deviation and the standard deviation both have the advantage of showing the average distance from each data value to the mean. So the disadvantage of the range is that it only shows the distance between the highest and lowest values. The disadvantage of the variance is that it comes out to such a large number, and it's difficult to understand what it's really showing about the data. And the advantage of the mean absolute deviation and standard deviation are that it gives you a sense of how far the numbers are from the mean on average. Let's now talk about the terms population parameter and sample statistic. A population parameter is a value that describes an entire population. A sample statistic is a value that describes a sample. Let's look at some examples. Before I do this, actually, let's look back at the last slide. Remember how all of these values here on this left side of the board were calculated with an entire population? Since they were all calculated with an entire population, they would all be called population parameters. So this range right here this variance, this standard deviation, and this mean absolute deviation would all be called population parameters. These same values over here, the range of the sample, the mean absolute deviation of the sample, and the variance and standard deviation of the sample would all be called sample statistics because they were all calculated with the sample. So let's go back over here. One example of a population parameter is a population mean, which is the mean of an entire population. What could be an example? Maybe the mean GPA of all 20,642,819 college students in the US. If you were able to record the GPAs of all 20,642,819 college students in the US, add those GPAs, and then divide the total by this number right here, your answer would be the population mean. And it would also be called a population parameter because it's a value that is calculated with an entire population. Another example is a population median would also be a population parameter. A population variance, meaning a variance that's calculated with an entire population. A population standard deviation. So if you recorded the GPAs of all of these college students, meaning you recorded the GPAs of every college student in the US, and then you used the answers to calculate a variance and a standard deviation, your answers will be called a population variance and a population standard deviation. And both of them would be called population parameters, just like how the population mean would be a population parameter. What about sample statistics? All of these values here are called sample statistics if they're calculated with data from a sample and not from an entire population. So a sample mean would be a sample statistic. And an example of a sample mean could be the mean GPA of 200 selected college students living in the US. So if I selected 200 college students, I recorded their GPAs, I added those 200 GPAs and divided the total by 200, I would get a sample mean, and that sample mean would be called a sample statistic. Also, if I found the median of the 200 GPAs, my answer would be called a sample median, and that would also be a sample statistic. If I calculated the variance of the 200 GPAs, I would have a sample variance. And if I calculated the standard deviation of 200 numbers, I would have a sample standard deviation. And that would also be a sample statistic. And there's actually symbols that are used for these different values. All of the population parameters have a Greek symbol. The symbol for a population mean is the Greek letter mu, which looks like a U, and it's pronounced this way. We don't talk about median. The symbol for a variance is sigma squared. That Greek letter is called a sigma. And a population standard deviation is just sigma. for sample statistics, they don't use Greek letters. The symbol for a sample mean is x. It's called x bar. It's an x with a bar above it. Sample variance is the letter s squared, and it's just called s squared. And then sample standard deviation is just s. The reason why this is just sigma is because it's the square root of the variance, and the reason why this is just s is because it's the square root of the variance. I won't go over the symbols for median. I wanted to also go over the symbols for sample size and population size. Those don't really fall into these categories, so I'll put them over here. Population size is a capital letter N, and sample size is a lowercase n. And if we wanted to go back to this slide right here, we could use some of those symbols. We said that the mean of the entire population was 66, so it would be mu equals 66. And the mean of the sample came out to 60.33. So over here we could say x bar, the sample mean, equals 60.33. And this was a population standard deviation. So we could say sigma equals 9.61. This standard deviation over here was a sample standard deviation, so we could use the letter s. We could say s equals 4.53. And one of the most important things as we go on is to remember that a population mean isn't the same thing as a sample mean, and also that population standard deviation isn't the same thing as a sample standard deviation. If you can remember those things, that'll make a lot of the later topics a lot easier. And since we don't collect data from entire populations, since they're too large to collect data from, hardly ever actually calculate population parameters. For example, no one would actually calculate the mean GPA of the entire college student population in the US. What we actually do is we collect data from samples and we calculate sample statistics. And then the sample statistic helps us get a rough idea of what the population parameter equals. For example, a person who's calculating this sample statistic right here is doing that to estimate what this population parameter over here equals. So the sample statistic estimates the population parameter, and that's just because, like we said, the purpose of collecting data from a sample is to learn about the entire population. And the sample statistic won't be exactly equal to the population parameter, but hopefully it'll be close enough to at least give us a rough idea of what it equals. Let's go back to this spreadsheet for a second. I want to talk about how we can use the descriptive statistics that we've been talking about to summarize this set of data. Each column of data is going to have its own descriptive statistics. I'll show you what I mean. The age column will have its mean, its median, its mode, its range, mean absolute deviation, variance, and standard deviation. So we could use this column of data right here, the age column, to calculate all of these values. And we'll get a certain mean, a certain median, a certain mode. We'll get one number for each of these. The number of units column will have its own mean, median, mode, range, and so on. So after we're finished calculating the values for the age column, we can move on and calculate all of the same values for the number of units column. And they're not going to necessarily come out to the same number that they did over here. For example, the mean of this column isn't necessarily the same as the mean of this column, and the median of this column isn't necessarily the same as the median of this column. We could then calculate all of the values over again for the number of children column. And all three of these are quantitative. All three of these are quantitative variables, which means that we can actually calculate all 7 of these values. But grade level is an ordinal variable. It's a variable that has categories that follow in order, but it doesn't have numbers that stand for amounts. So we actually can't calculate a mean for the grade level column. We can calculate a median and a mode. And if it's not quantitative, we can't calculate any of these measures of dispersion that we've been covering. So we actually can't calculate these last 4 values. So for this column, we could calculate a median, a mode, and that's all actually. Since it's a column of ordinal data, it's not quantitative. And what about this column right here? College major is a nominal variable, which means it's a variable that has categories, and the possible categories don't follow in order from lowest to highest. What that means is we can't have a median. We can't have a median because there's no way to put these values in order from lowest to highest. So we actually have a mode only. I wanted to do a quick demonstration to show why these values are able to measure the spread of the data. Here we have a column of data, and here we have the mean absolute deviation in yellow. That's just the average of the absolute deviations. We have the variance in red, which is the average of the squared deviations. And we have the standard deviation in green, which is the square root of the variance. Let's see what happens if we change 2 of the numbers to increase the spread of the data. The way I'm going to increase the spread of the data is I'm going to change this number to 5, and I'm going to change this number to 20, which will make the numbers a little bit more spread out. What's going to happen is when I change this number to 5, this data value is going to be further away from the mean of 12.5. Instead of it being 10 minus 12.5, it'll be 5 minus 12.5. So since this number will be further from the mean, it'll give us a bigger deviation right here. And also, if I change this to 20, this data value will be further from the mean of 12.5. So instead of it being 15 minus the mean, it'll be 20 minus the mean, which will give us a bigger deviation right here. So let's see that happen right now. Right, so these 2 deviations have increased. They've now gone up to negative 7.5 and 7.5. And since these 2 deviations increased, the absolute deviations here and here increased in the top and bottom rows. And because these 2 absolute deviations increased, the 2 squared deviations, meaning over here and over here, also increased. And then what happens now is that since these 2 absolute deviations have become higher, The average of the absolute deviations has become higher, which gives us a higher mean absolute deviation. And since these two squared deviations have gone up, it makes the average of the squared deviations higher, which gives you a higher variance. And if the variance is higher, then the square root of the variance also goes up, and then gives you a bigger standard deviation. If the variance goes up, the standard deviation has to go up along with it, because the standard deviation is just the square root of the variance. So we can see that when we added more spread to the data, these three values all increased. These three values measure the spread of the data, so as the data gets more spread out, these three values increase. And the reason they increase when the data is more spread out is because when the data is more spread out, the deviations, absolute deviations, and squared deviations become larger numbers. And since they become larger numbers, these three values go up.